طيب السلام عليكم شباب. إن شاء الله today we'll continue in chapter 6, the second law of thermodynamics. Last time we talked about the last two classes actually we talked about the second law of thermodynamic application to heat engine, and we came up actually with Kelvin blank statement for the second law of thermodynamics, and also we spoke about the application of second law of thermodynamics for refrigeration and heat pump system, and we came up actually with the Clausius statement applied for refrigerator and heat pump. Just to recall on those two statements, the first statement applied to heat engine, we said we cannot design a heat engine that can take the heat from high temperature source and convert all of this heat actually to work out without rejecting heat. And we said actually we cannot design a heat engine without heat rejection. So we have to reject some heat so that the system can work on a cycle to generate continuous work. And this is something related to the concept of operation, not related actually to the losses within the system. And as long as we have to reject some heat, that means actually in this case, we cannot design a heat engine with efficiency equal to 100%. And this is the Kelvin blank statement applied to heat engine. We have the second statement that we talk about applied for refrigeration and heat pumps, that we cannot design a refrigeration system that can absorb a heat from low temperature and reject this heat at high temperature without having work input, as actually heat cannot transfer from the low temperature to the high temperature. And the energy should be proceeding from the high energy potential to low energy potential, and to absorb this heat from low temperature and reject it at high temperature, we have to have work input. And the Clausius statement states that we cannot design this refrigeration system without work input in this case. And actually the two statements for the second law of thermodynamics applied for heat engine or applied for refrigeration systems, the two statements are identical. And any violation actually in one statement should lead actually to a violation in the second statement. Right, let's look here. In this example, let's see how we can actually, if we have a violation, let's say in Kelvin blank statement, how this actually can lead us to a violation in the second statement, which is the Clausius statement. So let's consider here we have a heat engine. This heat engine has efficiency equal to 100%. So in violation of the second law of thermodynamics, in violation of the Kelvin blank statement, it converts all of the input heat into work out in this case. So this is a clear violation for the first statement. So let's say this heat engine is driving a refrigeration system. So the work out of this heat engine is the input to the refrigeration system. And this refrigeration system takes the heat from Q low, absorbs the heat at low temperature and rejects this heat at high temperature in this case. But let's see how we can have, if we have a violation in one of the two statements, this can lead us actually to a violation in the second statement. So let's consider this is actually the heat engine. This heat engine, let's say it absorbs heat at high temperature. So let's say this is Q high 1, and it gives actually all of this heat actually converted into work in this case. Okay, and this work out of the heat engine that clearly violates the second law of thermodynamics statement, the efficiency in this case is equal to 100%. So this is a clear violation of the Kelvin blank statement. Let's say the work out of this engine will be driving a refrigerator. So we have a refrigeration system that takes actually Q low. Let's say this is actually Q low 2, and actually takes this heat and reject this heat at Q high at high temperature. Let's say actually this is Q high 2. Okay, and let's consider the first system, which is the heat engine, and apply in this case the first law of thermodynamics. The system is working actually on a cycle, so we have energy in minus energy out equal to the change of energy of the system. The system is working on a cycle, so this the change of energy, final energy minus the initial, should equal to 0. Or what we can say actually energy input to the system should equal to energy out from the system. If I look at this heat engine, what is input? We have Q high 1. That should equal to the output, which is the work net in this case. And this is actually based on applying the first law to the heat engine. Let's apply the first law to the refrigeration system. Look here, what is coming in and what is leaving. So in this case, we have work net plus we have Q low, which is Q low 2. What is leaving is actually is Q high 2. But we said work in it is the same as Q high 1. Then in this case we have Q high 1 plus Q low 2. That should equal to Q high 2 in this case. Okay? Or Q high 2 should equal to Q high 1 plus Q low. But let's just redraw this refrigerator system. We have here actually work in it, which is Q high 1 equal to Q high 1. And here we have Q high 2, Q low 2. And here actually out the output we have Q high 2, which is equal to Q high 1 plus Q low 2. Okay? But Q high, let's look at this system. What is coming in? Q high 1 plus Q low 2. That should equal to what is leaving, which is Q high 2 plus Q low 2. This Q high 1 will go with Q high 1. Then in this case, we'll come up actually to a result that we have a refrigeration system that takes Q low 2 and gives actually Q low 2. We have Q low 2 and Q low 2 at the outlet section in this case. So we result actually in a refrigeration system that takes the heat from a low temperature and drives this heat actually deliver it at high temperature without having work input. So actually, if we have a violation of the second law of thermodynamics for the Kelvin Planck statement for a heat engine, that means actually also we have a violation that leads us to a violation in the second statement, which is applied to the refrigerator and the heat pump system. So the two statements are identical. As a matter of fact, this second law of thermodynamics, we don't have mathematical proof for the second law of thermodynamics. But actually, any experiment has not gonna actually throw any violation for the second law of thermodynamics or the first law of thermodynamics. And this is a clear proof actually that the first law of thermodynamics and second law of thermodynamics are actually correct. However, we don't have a mathematical proof either for the first law or for the second law of thermodynamics. Okay. We have a kind of machine which we called actually as perpetual motion machine. Those perpetual motion machine are machines which are in violation either to the first law of thermodynamics or to the second law of thermodynamics. If this machine is in violation to the first law of thermodynamics, we call it actually perpetual motion machine 1. If it is in violation to the second law of thermodynamics, we call it perpetual motion machine 2. But actually, those machines, they are just actually designed. They never come actually to operation because those actually machines just are in violation in the first or the second law of thermodynamics. Usually, they have been submitted as patent to the patent offices, but all of the patent offices actually stopped receiving designs that violates either the first or the second law of thermodynamics. Because actually, we don't have mathematical proof, as I told you, for first or second law of thermodynamics. However, actually, we don't have actually any machine that came into operation in violation to either first or the second law of thermodynamics. Okay, so you have heard, I think you have heard about actually in our TVs in countries like our countries, actually you hear about any child that is coming actually with a design. He say we have a system that an engine that will be running with water and it will be running without actually paying any kind of energy to the system. So what we should do in this case, we should just apply the first law of thermodynamics. All of this actually engine should be working on a cycle. So that means the energy input should equal to the energy output. So nothing will be working actually without input energy. Even the output energy, as we cannot design a system of efficiency equal to 100%, that means the output energy should be less than the input energy. Okay, so we cannot design a system without input energy. So if you look at any invention, you have to look from the side of first law of thermodynamics and the second law of thermodynamics. Here is an example for the perpetual motion machine 1, which is a virtual machine, just a design. It never come to operation. This machine, this guy actually who presented this design, he said, instead of burning fuel inside the boiler here to have heat added to convert the water, actually the water into steam, then we can drive actually this steam turbine. He said, we will take actually this steam turbine is connected to an electric generator to generate electrical power output. I will take part of this power output to drive the input system. So usually, as we told you, there is actually efficiency for any heat engine, which should be less than 100. That means the output should be less than the input. Now he is taking part of the output, which is less than the input, to drive to be the input to the system. Okay? And this system can never work. Because if you look at this system and apply the first law of thermodynamics, energy input should equal to energy output. Look at this system from outside. Do we have any kind of energy input to the system? We don't add fuel, just actually we take the part of the output to be actually to heat up. This is a kind of electric heating coil to heat up the water to convert it to steam. But if you look from outside, we have designed a system without any input. Just this system will be providing us work output, the remaining electrical work, and we have actually heat is rejected. So this is a perfect system if we can have that this system will don't have any kind of input, and it will give us actually electrical power, and the heat is rejected here without any input to the system. So this is a clear violation for the first law of thermodynamics. The perpetual motion machine 2, which is violation to the second law of thermodynamics. This system is a steam power plant without a condenser, so we don't have heat rejection. That means all of the input heat will be converted to work. That means the efficiency is equal to 100%. And this is actually a clear violation to the Kelvin-Planck statement applied for a heat engine. As I told you, those machines just are actually virtual machines, just designed. They never come to operation because they are in violation either to the first or the second law of thermodynamics. One of the main uses, as I told you, for the second law of thermodynamics is that we can apply a Carnot cycle either to a heat engine or a refrigeration system. Carnot cycle actually is a cycle in which actually all of the processes are reversible processes. We don't have any kind of losses within the system. That means actually based on this Carnot cycle, if it is applied to a heat engine in this case, the efficiency of this heat engine should be actually the maximum efficiency of the engine in this case. And this maximum efficiency should also be less than 100. It cannot be 100. Okay? But this should be, if we assume we don't have any kind of losses, that means the efficiency is equal to 100%. If we apply this Carnot cycle, as all processes are reversible, then it can be applied for the refrigeration system as well. If we applied it on the refrigeration system, then we can calculate the maximum coefficient of performance of this system. And the idea here is that we can calculate the limit of this system, the limiting state, which is the maximum efficiency. We don't have any kind of losses. In this case, I can calculate the maximum efficiency for a heat engine, and also I can calculate the maximum coefficient of performance of a refrigeration or heat pump system. Then we can compare those limiting state to the actual state. If we have a heat engine with efficiency equal to, let's say, 60%, and the maximum efficiency based on the application of the Carnot cycle on this heat engine is equal to, let's say, 75%. That means actually 60 from 75, this is actually a very close value. That means this system is efficient in this case. But if the actual efficiency, let's say, is 40% and the maximum is 75, that means actually we have big gap in this case, and that means we have actually a large amount of losses within this system. And this is the idea of the application of the Carnot cycle, which is a cycle in which all processes are a reversible process. But what is the definition of reversible process? Reversible process is a process actually that can be reversed without leaving any trace, either actually on the system or on its surrounding. So this process, as long as we don't have any kind of losses, so the process can proceed in one direction, and it can be reversed to the other direction. Like what? Like the frictionless pendulum. If we have a frictionless pendulum, it will be going in this direction. We don't have friction, then it will be going back to the reverse direction based on the effect of its weight, and then it will be going forward and backward without actually stopping in this case, because the process does not have any kind of friction. This is a reversible process, is not a real process. It cannot be actually a real process. We cannot have a process that is reversible. This is just an assumption, okay? We cannot have a frictionless pendulum. Friction is always there, okay? But this is an assumption. Also, like the process which we have defined earlier in chapter 1, which is called the quasi-static process, quasi-static expansion. If we have this process is done very, very slowly, so that equilibrium is attained everywhere within the system through a compression process. Then if we have done also reverse the process to be expansion in the reverse direction, but we are moving this piston very, very slowly, then equilibrium is also attained everywhere. Then in this case, we can say actually this is a reversible process, in which actually the process can be reversed without leaving any trace on the system. A reversible process also, if we have a wall here in a tank, this is a movable wall. If we are moving this wall actually to expand, in this case in the expansion direction, then in this case if we are moving very, very slowly, then in this case the surface of the water will be flat, and this process actually can be reversed in the reverse direction also, done very, very slowly. Then in this case we can say this process is a reversible process. But if we are moving this wall a little bit fast, then in this case the surface of the water will be deflected. In this case it will be curved, and in this case the process cannot be reversed in this case without leaving a trace. Okay, so in this case water will be moving, then we will have more friction, and the temperature of the water in this case will be raised. The entropy also will be raised within the system, and we cannot reverse this process. But all what I want to say, Shabab, is the reversible process is not a real process. This is actually an ideal process or virtual process in which we assume we don't have any kind of losses. But why we are considering this process as long as it is a virtual or non-real process? Because for two reasons. This process actually, when we assume we have a reversible process, that means I will not be calculating actually all kind of losses within the system, like the friction losses and heat losses from the system. So in this case, it will be easy to analyze in this case, apply the first and second law of thermodynamics. Also, this process serves as an idealized model, or gives us actually the theoretical limit of the system. As I told you, we can apply Carnot cycle, which is a reversible cycle of reversible processes. We can apply to a heat engine, then we can calculate the maximum or the theoretical limit of the maximum efficiency of this system. And then we can compare it actually with the actual value to give us indication about the losses within this system. Okay. What kind of irreversibilities or losses that we can have within a system? Okay. We have different kind actually of irreversibilities or losses within the system that may result actually in losses. Those irreversibilities, first of all, we have friction. So let's say we have a piston that is moving inside a cylinder. Then we have a friction between this piston and the cylinder wall. Also, we have friction between the molecules, the gas molecules, and the piston itself, and also between the gas molecules and the cylinder wall, while the motion, while expanding or while compression. So in this case, we have to have a kind of friction with any kind actually of motion. Any kind of motion should result actually in friction losses. Also, when we have unrestrained expansion, like if we are expanding solid substance like steel or something, if we are deforming this steel, so we cannot return it back to the original shape unless we apply a certain kind of processes, so that actually we have to melt it all first of all, and then we have to reshape it back. So in this case, we have to exert more energy in order actually to get this steel bar to the original state. So we cannot restrain actually retain the unrestrained expansion of solid. Also, mixing of two fluids is actually a totally irreversible process. If you are mixing, let's say, the gas mixture here actually is atmospheric air. We have oxygen plus nitrogen plus helium plus some other gases. But actually, this mixing process, if we want to separate the gases, let's say we need only O2 plus only pure nitrogen, we separate all of these gases. In this case, we have to use membrane system. Membranes are actually a solid substance which are selective to a specific gas. Those membrane actually can separate the different gases, but those membranes to be activated for the separation, they want actually to be heated up to a certain temperature level. So that means we have to pay energy in order actually to separate the gases again. So the mixing process of gases cannot be reversed again unless actually we have to exert energy in this case. Also, Shabab, the heat transfer process across any temperature difference, this process cannot be reversed anyway. So let's say heat can be transferred from high temperature to low temperature, from 20 to 5 degrees C. But can we reverse this process? Can we have heat transfer from 2 degrees C, from 5 degrees C to 20 degrees C? So this is actually impossible process. So in this case, to have heat addition, to have a reversible heat addition process, that means actually this process should be done under constant temperature, because whenever we have temperature difference, the process cannot be reversed in this case. So the only way to have a reversible heat addition process is through actually a constant temperature heat addition in this case. If we look here for this heat engine, for this boiler, we said we have to add heat in this case to the boiler to convert the steam from the liquid to the water. If this heat added under difference in temperature, so this process cannot be reversed. So the only process for heat addition or heat rejection process, for having a reversible heat addition or heat rejection process, the heat addition or heat rejection should be done under constant temperature in this case. Okay. So this is also a kind of irreversibility when we have heat losses from the system over a temperature difference. Also, when we have electrical resistance, when we have electric heating coil or something, if we apply electrical current, we can convert it into heat in the electric heating coil. But if we heated up the electric heating coil, we cannot get actually any electrical current in this case. So this process is also a irreversible process, and it is a source of irreversibilities within the system. Also, inelastic deformation of solid. As we said, if we are deforming actually any kind of solid, we cannot actually retain it back unless actually we exert more energy to get it back to the initial situation. Also, chemical reaction are totally irreversible process, because we convert, let's say, we are burning fuel, methane, with oxygen. So in this case, if we are burning methane with oxygen, we'll get some heat is released, and this methane will be converted to carbon dioxide plus some other constituent, including H2O, water vapor plus NO plus NO2, and some other gases actually if we are burning this methane with air. So that means we have converted the fuel into combustion product. But actually in this case we cannot, if we added actually heat to the combustion product, in this case actually we cannot get back to the fuel again, like the engine of your car. We burn the fuel to get exhaust gases and drive your engine. But actually in this case, if I reverse the process, in this case, if we heat up the exhaust gases or reject the heat exhaust gases, in this case we cannot get the fuel back. So chemical reaction, we have some species that are totally converted to other species in this case. So this process also is a kind of irreversible process. We do have the reversible process. We call it internally reversible process when we have actually no irreversibilities occur within the system itself. We have externally reversible process when we do have no irreversibilities or any kind of losses occurs actually outside of the system boundary. We can call the process as totally reversible process when we don't have any kind of irreversibilities either within the system or actually outside the system for the surrounding, outside the boundaries of the system for the surrounding medium in this case. So we don't have any irreversibilities inside the system or outside the system in this case. We call this process in this case as totally reversible process. Okay. Here is an example of internally reversible process. As we said, the only way to have a reversible heat addition or heat rejection process is through actually an isothermal process. When we can have isothermal heat addition? So usually when we add heat to a system, its temperature will be raised in this case. How come we can add heat and the temperature will remain constant to have reversible heat addition process? This can happen only while the phase change process. In this case, you add heat, but this heat is latent heat. It will be used actually to convert the phase either from liquid to the vapor phase or from the solid to the liquid phase without actually temperature rise in this case. Also, we can have heat is rejected from the vapor so that it can be converted, saturated vapor can be converted to saturated liquid in this case. So we can have heat addition or heat rejection while the phase change process without having actually temperature rise. So in this case, if we have a fluid let's say at 20 degrees C. This is the saturation temperature of this fluid. So we have a boiling or phase change of this fluid under this temperature. So if heat is added from an external source, this will be a latent heat. So the temperature here will remain the same, and the liquid will be converted to vapor in this case. So we don't have any change within the system. So we call this process as actually as internally reversible. We don't have rise in temperature. But what about externally? If we are adding this heat from a source, which is at the same temperature, 20 degrees C, that means we don't have temperature difference. So this process is also externally reversible. So internally reversible, we don't have temperature difference inside. And externally reversible, we don't have temperature difference between the surrounding and the system itself. That means this process is totally reversible process. But if we are adding heat from a source that is existing at 30 degrees C, so that means we have temperature difference between the external system and within the system itself. This is 30, this is 20. So this process actually is irreversible, externally irreversible. Okay, so we have irreversibilities outside of the system boundary. But inside the system, while the phase change, when we add heat, the temperature will be remaining the same. So we call this process as internally reversible. But it is not totally reversible, as we have external irreversibilities due to this temperature difference between the surrounding and between the system itself. Okay, so totally reversible process mean actually we don't have any kind of irreversibilities either within the system or outside the system boundary between the system and its surrounding in this case. Internally reversible, we don't have a change within the system, any kind of irreversibilities within the system, but we have external irreversibilities in this case. So we call this process as internally reversible process. As I told you, our talk about the reversible or irreversible process, we are just introducing to the CARNOT cycle, which is a cycle actually with all processes are reversible process. So those processes, as they are reversible, so that they cannot be applied for a heat engine to convert the heat into work, or we can reverse the case for the refrigeration and the heat pump system to convert the work into heat transfer in this case. And in both cases, I can calculate the maximum performance of the system, and we can compare it actually with the actual value. This cycle, شباب, CARNOT cycle can be applied for closed system cycles, like the internal combustion engine in your car. This is a piston cylinder device. Piston cylinder device, this is a kind of closed system. If we considered only one cycle, so it will be a closed system. We have fuel is burned, then we add heat. As we said, to have this process reversible, heat addition, it should be done under constant temperature from state 1 to state 2. Then actually due to this heat addition, the pressure and temperature inside here, the tank temperature will be remain the same T high, but the piston due to the increase in pressure will be pushed actually, and due to the heat release of combustion will be pushed actually to go down in the expansion process. And then this expansion process, it will be moving the crankshaft to move the car. Then in this case, as the piston, this process from 2 to 3 is expansion. Then from process 3 to 4, we want to actually to have the piston back at the top and actually exhaust gases, take the exhaust gases outside of the engine. Then we can have fuel again and repeat the cycle. Then the compression process from 3 to 4. Also, it is similar to the expansion process, which should be actually adiabatic, should not have any kind of heat losses, either for the expansion process from 2 to 3 or for the compression process from 3 to 4. It should be adiabatic, and it should be this movement of the piston, so it should be frictionless. Adiabatic and frictionless, that means the process is isentropic in this case. So it should be isentropic expansion and also isentropic compression in this case. Okay, the compression is from 4 to 1. The process from 3 to 4 actually is the heat rejection process by rejecting the exhaust gases. This heat rejection as well should be done also under constant temperature, which is T low in this case. This system, the CARNOT cycle, can be applied for closed system cycle, and it can be applied also for the open system cycle, like the case actually of the steam power plant, and also for the refrigeration and air conditioning cycle. Inshallah, next time I will be talking about this cycle in details and its application to heat engine and also to the refrigeration cycle. Okay, that's all for today. So inshallah, we'll meet next time.